Welcome back to the channel, guys. Today, I'm really excited to present a project where I will walk you through step by step how to manage an end-to-end machine learning system capable of detecting and blocking malicious traffic to your website in real time. Like all my tutorial, you can find the entire project and is fully available and downloadable from the GitHub link in the description below. So you will be able to try everything out of yourself and experiment with all the technologies we cover. So in this tutorial, we'll dive into both theory and practice of machine learning, covering the models used for feature selection and binary classification. But we'll also focus on the infrastructure. I'll show you how to build a complete CloudFormation stack for fully automated deployment with just a few clicks, introducing you to the power of infrastructure as code. So this project features two fully automated CI/CD pipeline with AWS code pipeline, so you can build and deploy your application with a simple push to GitHub. So we will see how, starting from a YAML template, we can create the entire infrastructure with just few clicks, and with only two pushes to GitHub, we can trigger the deployment process almost magically and have the system up and running. So the solution is structured around two main servers that actually are EC2 instances. So the first hosts the ML service, which comes packed with three main features, including batch training with model testing, incremental stream training, and real-time prediction. This lets you train and test your model using historical data or by generating real traffic directly on your web app. The second server manages your application and website security. Throughout the tutorial, we'll build everything from scratch. So we'll walk through the Python code together. I'll explain step by step how each component works, and we will watch the system working in real time, both for streaming, training, and for predicting and blocking malicious traffic. So this is going to be a truly exciting tutorial. We'll simulate a real-world attacks like DOS, fuzzer, analysis, backdoor, exploit, shellcode, worm, and more. So we will use these attacks to test our defenses, train the model, and automatically block suspicious IPs. So finally, I will explain the theory behind the models used, autoencoders, and ORC for dynamic and feature selection. So get ready for full journey into security, machine learning, cloud automation. Let's get started. If we take a look at the feature list, you can see it's seriously long and extended. So first off, at its core, this platform brings real-time network attack detection. So it can classify traffic as normal or malicious with a sub-second response times, giving you instant predictions. So it doesn't just say yes or no. You also get like a probability score that tells you how likely the traffic is to be an attack, and it supports a wide range of attack types. So under the hood, we have advanced feature engineering. So the model extracts over 23 different network traffic features, but of course you can customize, you can increase, you can add more, and actually automatically detects feature types and handles both numbers and categories. Categorical variables are smartly encoded even when they are previously unseen, and features are scaled for stable learning. For feature selection, we are using an ORC-based selector powered by autoencoders. The system tracks feature importance dynamically, adapts in real time using exponential moving averages, and updates its selected features as new data streams. For classification, we use an SGD classifier. It's quite simple. For binary classification, it works pretty good. That actually supports incremental learning. That's the special feature. It handles class imbalance and provides interpretable probability scores as well as feature importance. When it comes to training, you get actually both batch and real-time streaming options. So the batch pipeline automatically analyzes your data, balances samples, tracks progress, tunes threshold, and exports training history. Meanwhile, stream training lets you update the model on the fly, adapt to new attack pattern, and monitor performance in real time with the checkpoints for safe persistence. For network monitoring, the platform does a real-time packet capture with full flow analysis, tracks TCP states, support automatic interface detection, and extracts dozens of packet-level features including timing, sizes, rates, and protocol-specific metrics. On the infrastructure side, the project is ready for production with AWS CloudFormation template that lets you deploy scalable EC2 instances with load balancers, auto-scaling groups, security groups. The CI/CD pipeline uses AWS code pipeline with DDoP triggers for automated deployments, full test validation, blue-green releases, and multi-environment support. So the service itself runs as a modular Flask API, following microservices best practices. All right, let me show you a quick demo of detecting a denial of service attack. We simulate this kind of attack. This is not a DDoS, it's not distributed, it's just a simple, just for demo purpose. So usually hackers use a better approach. For this tutorial is enough. So here we have our server running our ML service, okay, for inference. Here we have our Flask endpoint. And while this other server contains the web application exposed to the internet with the domain, I'm currently using my site, that is thevergolabs.com. So going to use this for the demo. So the web app is here in this server. With the web app, we have also a packet sniffer application that actually generates data flow, as you can see here, and sends API call to this ML service for inference. So we will explore the project and code, of course, in detail in the following section. But now I just want to show you this demo. So now locally I have this script that simulate different network attack. For now we just use we just try the DOS with just a really small duration and 300 threads. Okay, later we will see in detail one by one. I'm using already a pre-trained model with thousands of balanced records between labels 0 and 1, meaning normal traffic and attack traffic. So let's see what happens when I launch the DOS attack. Let's try. So we set DOS here. Okay. So as you can see, the inference response logs from the ML service show the result of numerous data packets being processed simultaneously. Are all really high. Okay, so the prediction is all network attack. Okay, probability is 95%, 94%, 98%. So it's really sensitive to the DOS attack. 99, 90. Yeah, it's all high. As the attack finish, it start to retrieve the normal traffic that actually get my SSH traffic from the port 22. It also get the traffic generated from some visitor from my website. Now we should see the probability is going to decrease. Yeah, is 55%. Is just 15%. So the prediction is 0. Normal traffic is just really low. Prediction 0. Let's try to navigate the website to generate some data. More data. Okay. See, you can see that. So let's generate some traffic from the website, just visiting different sections. See, we have prediction 0, just 7%, 5%, 2%. So it's just predicting normal traffic, and actually it's true, it's correct. Let's try another DOS attack. So we can see it's going to increase again. Go. It's overflowing. A lot of packages. We go. Yeah. If we evaluate for each flow, 98%, 97, 98, 98, 97. Here we go. So let's see how to build this system step by step. So now we will see how the ML pipeline is structured. So how each component processes network traffic data to identify the malicious patterns. So we are going to focus on the specific implementation and mathematical principles used in our system. So we start from the data preprocessing pipeline. Our pipeline handles network traffic data containing both numerical variables like packet counts and byte size and categorical identifiers like protocol types like TCP, UDP, 4 numerical columns with fewer than 5 unique values relative to total samples. We treat them as categorical since they likely represent flags or discrete states. So the core transformation uses label encoding. Each unique categorical value gets assigned a unique integer identifier, creating a one-to-one correspondence between categories and numbers. For example, as you can see, TCP can be 0, UDP 1, or other category like DNS, SSH. So the encoder actually learned this mapping during the initial training phase by scanning all the unique values in each categorical column. For numerical features with extreme ranges exceeding 10,000, we apply a logarithmic transformation using this formula. Okay? Actually, we compress the scale before further processing. So the small constant you can see here prevents taking the logarithm of 0, which will be undefined. So this transformation is particularly important for network traffic features like byte counts or packet sizes that can span several orders of magnitude. The logarithmic compression actually brings these extreme values into a more manageable range. After this, we are going to apply the robust scaling. Then it normalizes all numerical features using this formula. Its scale is x minus median and divided for IQR, where IQR actually represents the interquartile range calculated as Q75 minus Q25. This scaling approach fundamentally differs from standard z-score normalization, which uses mean and standard deviation. So the median actually represents the middle value when all samples are sorted, making it completely immune to extreme outliers, since sometimes attacks represent outliers that should distort the normal traffic scaling. The robust scaler actually maintains several key characteristics that make it ideal for network attack detection. The incremental adaptation mechanism allows the scaler to track concept drift in network traffic patterns, such as changes in typical connection size or packet rates, without being disrupted by intermittent attacks. The next step is the autoencoder. Actually, we use this component for feature selection. Our autoencoder actually serves specifically as a feature importance detector rather than a general compression tool. So the network architecture implements a simple hourglass structure with input dimension matching our preprocessed feature, typically around 100-200 feature compressed to a hidden dimension of 32 neurons here, and then reconstructed back to the original size. So the encoder applies the transformation with the ReLU. So we have all the weight from the encoder multiplied for the input, and we add the bias of the encoder, where X actually represents our preprocessed network traffic feature, and H become the compressed representation. So the decoder reconstruct, okay, using the X reconstructed, that is equal to W encoder and multiplied for H, and we add the bias for the decoder without the activation, since we need actually linear reconstruction of the original feature. So the critical insight for network attack detection lies in the reconstruction error calculation. So we compute per feature absolute errors using error I equal to module of X original I minus X reconstructed I for each feature position. So features that consistently produce high reconstruction errors indicate patterns that autoencoder struggles to compress, suggesting that this feature actually captures unique characteristics important for actually distinguishing normal from attack traffic. So the training occurs exclusively on normal network traffic. When we encounter a sample with label 0, actually represent normal traffic. So we perform the forward pass, calculate the mean square error loss, that is a MSE, that actually is represented by this form, where we calculate actually the difference between the input X and the reconstructed. It actually compute gradients through backpropagation and update weights using Adam optimizer. So the attack traffic with label 1 never trains the autoencoder, since we want the model to learn only normal. After this, we are going to apply the ORC, actually the online reconstruction-based feature selector represents a novel approach to identifying the most informative feature for network attack detection by leveraging the reconstruction capabilities of our autoencoder. So the fundamental insight behind the ORC is that features which are consistently difficult for the autoencoder, okay, to reconstruct accurately contain unique patterns that distinguish attack traffic from normal traffic. So when the autoencoder trained exclusively on normal network traffic encounters features that deviate significantly from learned normal patterns. So it struggles to reconstruct this feature accurately, producing high reconstruction errors. So the online reconstruction-based feature selector maintain actually an exponential moving average of reconstruction errors for each feature position, creating a continuous assessment of feature importance over time. So starting with the 0 score for all the feature, the system updates using the formula ORC new is equal to beta multiplied for ORC old plus 1 minus beta multiplied for error current, where beta actually is our smoothing factor, typically is 0.99, giving much more weight to historical patterns while incorporating new information gradually. So this exponential weighting scheme ensures that temporal spikes in reconstruction error don't immediately dominate the feature importance scores, while persistent reconstruction difficulties accumulate significance over. So the choice of beta equal to 0.99 means that each new reconstruction error contributes only 1% to the updated ORC score, while 99% comes from the accumulated history of reconstruction error for that feature. So the mathematical intuition behind using reconstruction errors as feature important indicators stems from information theory and compression principles. With the ORC, we are going to calculate a final feature mask that we are going to apply before the SDG classifier, sorting all features by their ORC scores in descending order. So the formula, top indices, arg sort minus ORC score, and 0 top key, actually select the key feature, okay, with the highest reconstruction errors, where the negative sign in arg sort ensures a descending order sort. So these indices get sorted numerically to maintain consistent feature ordering across the pipeline, preventing downstream models from being confused by changing feature position. So after selecting only few features, by using the ORC, we are going to put them inside the SDG classifier. So the first step is to train the autoencoder, select the feature, and after this training is complete, we start to train the SDG classifier using only a subset of selected feature depending on the ORC ranking. So our SDG is a stochastic descent gradient classifier, and it uses actually partial fit for true incremental learning, essential for streaming network traffic analysis. So the linear decision function fx is equal to wx plus the bias, where w represents learned feature weights and b the bias term. For binary classification, we predict that when the fx is bigger than 0.5 and normal traffic otherwise. The classifier employs log loss with this formula. So this formula actually applies the gradient descent, and it is a classic formula that uses the adaptive learning rates starting at 0.01 and automatically adjusting based on convergence pattern. These two formulas manage the class imbalance, so we track the cumulative counts of normal and attack samples, computing weights as a weight normal and weight attack. So this inverse frequency weighting ensures that the model doesn't become biased toward the majority class, typically normal traffic. So at the end of this pipeline, we predict if is label 1 is malicious traffic or is an attack, and 0 is normal traffic. So now comes the true challenge. That actually is, having understood the theory and concept behind our network attack detection system, we face the complex task of implementing these mathematical principles into fundamentally different operational modes. So the first challenge lies in creating a batch training pipeline that processes complete dataset in a single training session. And the second mode is more demanding challenge because it involves in building an incremental training pipeline that continuously learns from streaming network traffic data arriving in real time from monitoring servers. Here we have access to the entire historical dataset of network traffic. But the incremental training pipeline, however, operates under fundamentally different constraints and assumptions. The network traffic arrives continuously as a stream with no guarantee of class balance, temporal distribution, or data completeness, so we have a different kind of challenge. All the components must adapt to these two different cases. The system consists of two main training approaches, and we have the batch training in batch train pi, is the initial training on historical data, and we have also the incremental training that the entry point is in ML EC2 service and is a real-time learning from streaming data. So the batch training is the foundation of our system. It processes large datasets offline to create the initial machine learning models. This approach allows us to train on balanced datasets, optimize model parameters, and calculate also optimal attack detection thresholds, and create also comprehensive baseline models. Actually, it elaborate the dataset that is in CSV. So we have two files, that one is for training and another is for test. So let's walk through the complete batch training workflow step by step. The script first set up two important Boolean flags that act like switches, actually. That is a execute training that determines where we'll actually train new models from scratch, while execute test controls whether we evaluate our models after training. So these flags give us flexibility. Maybe you only want to test existing models without retraining, or perhaps you want to train but skip testing for now. Let's see the main function. What happened here, actually, it serves as an orchestrator for our entire training pipeline. It starts by calling getDefaultConfig, which loads all the essential settings from our configuration file. Things like where to find the training data, what parameter to use for the neural networks, and where to save our trained model. And next, we validate our configuration using validateConfig. This is actually crucial because we want to catch any problems. Maybe a file path is wrong or something else. And then we have also print config summary that display all these settings in a actually human readable format. And finally, we create our class that is batch trainer as an instance, passing in our validated configuration. This trainer object will become the central hub that manages our entire machine learning pipeline, from loading data to saving the final trained model. Let's see the batch trainer. This constructor actually is where we set up the foundation of our entire machine learning system. When we create a new trainer instance, it actually initialize all the components we'll need throughout the training process. So the self-config stores our configuration settings, while variables like data config and pros config will later hold information about our dataset structure and preprocessing. Notice how we initialize all our machine learning models to known, because the preprocessor, autoencoder, ORC selector, and the SGD classifier. This is actually intentional because we don't know at the exact dimension and parameters we will need until we analyze our data. So it's like preparing empty containers that we will fill with the right components once we understand our dataset better. So the trainer also set up storage for our training data with the self all samples and self all labels as empty lists. So these will eventually hold all our network traffic samples and their corresponding labels, normal or attack. So this initialization part is clean and organized. We are preparing everything we need without making assumption about the data we haven't seen. We go to execute training. As you can see, we have different steps here. We first validate, we analyze the data, set up a processing, initialize the models, loading training data and balance dataset, and then we process samples through pipeline. We train the classifier here, and we calculate the optimal threshold. Okay, and at the end, after we print everything, we save the models and metadata directly in artifacts. folder and we print a comprehensive summary. Okay, let's see the validate configuration. That is a simple function. And then we go to the next step, that is data analysis. Go to analyze data and we initialize here. We need to understand what we are working with before we can build effective models. So the method starts by calling print data summary, which gives us like a comprehensive overview of our dataset structure, including things like column types, value ranges, and potential issues. So the create feature config function is particularly helpful. Actually, it automatically analyzes our CSV file and categorizes each column as numerical, categorical, or a potential label. This actually saves us from having to manually specify the data types for every column. So the code that makes an intelligent decision, if the user has specified particular feature to use, it respects that choice. But if not, it falls back to the auto-detected feature. Actually, we have two ways to set it. One important validation step happens when we check the labeled column. The system compare the user-specified label column against the automatically detected label candidates. If there is a mismatch, it warns the user. This actually catches common mistakes like typos in column names. And finally, the method self-available calls, which will be the actual feature columns used for training, excluding any columns we don't want, like IDs or timestamps and the label column itself. So after this, we invoke the setup preprocessing, is where we bridge the gap between raw data and machine learning algorithm. The preprocessing pipeline handles this conversion intelligently. So the code first checks if the user has provided custom preprocessing settings, but if not, it creates a sensible default configuration. Notice the choice of label encoding for categorical features. This is more memory efficient than one-hot encoding and also works well with our incremental learning approach. So the actual preprocessing happens when we call self preprocessor fit on a sample of our data. This is where the preprocessor learns the categories for each categorical column and calculates scaling parameters for numerical columns. So the sample size is configurable, but we only need enough data to see the range of values. We don't need the entire data set. So after fitting, get feature info actually tells us exactly how many features we'll have after preprocessing, which is essential for initializing our neural networks with the correct input dimensions. So the next function is initialize models. The model initialization is where we bring our machine learning components to life, actually. So the code first check whether feature selection is enabled through the apply feature selection flag. So this is important because feature selection adds a complexity but can significantly improve performance by focusing on the most relevant network traffic characteristics. So when feature selection is enabled, we initialize three key components. So the autoencoder that is configured with the in that equal to our preprocessed feature count. This neural network will learn to compress and reconstruct normal network traffic patterns. The D hidden parameter determines how much compression happens in the middle layer, so typically set to about half at the input size. The online reconstruction-based feature selector is initialized with the full feature space and will gradually learn which features are most important based on reconstruction errors from the autoencoder. Notice it's set to batch mode, which means it will process all training data before making the final feature selection decision. And next, we have the SGD, the stochastic gradient descent. Really standard classifier, linear classifier, is our final decision maker that will distinguish between normal and attack traffic. It's configured for incremental learning, which means it can update its knowledge as new data arrives without forgetting what it learned before. So finally, we create the artifacts directory where all our trained models will be saved. Next step is loading training data. After this, loading training data is actually where we finally start working with our actual network traffic data. The method uses a streaming approach with the stream CSV row. instead of trying to load a potentially massive CSV file into memory all at once, actually it reads the data in chunks of 5,000 rows. So this prevents memory overflow and allows us to process data sets that are larger than our available RAM. As each chunk is processed, the code separates the features, the network traffic characteristics we'll use for prediction from the labels, whether each sample represents normal traffic or an attack. Actually, the progress reporting every 20,000 samples is helpful for long-running processes. So it shows both the number of samples processed and the processing speed in samples per second. So once all data is loaded, the code performs a crucial analysis of a class distribution using counter. Okay, this tells us how many normal versus attack samples we have, which is essential information for understanding potential bias in our dataset. So the imbalance ratio calculation reveals whether we have a balanced dataset or if one class significantly outnumbers the other. So this will influence our balancing strategy in the next step. And the next step is balanced dataset. Okay, we find here. This is really a critical step, really important especially for binary classification. It addresses actually one of the most common problems in cybersecurity machine learning, class imbalance. In real-world network traffic, normal traffic vastly outnumber attack traffic, sometimes by ratios of 100 to 1 or even more. So if we train on this imbalance, that our model will become biased toward predicting normal for everything. So achieving high accuracy but missing most attacks. So the solution implemented here is undersampling, where we reduce the majority class to match the size of the minority class. So the code first separates all the samples by their labels, then uses resample to randomly select a subset from each class. So the random state that is equal to 42 ensure reproducibility. You will get the same balanced dataset each time you run the training. Actually, it's the seed. The shuffling step is crucial because after balancing, all normal samples will be grouped together, so followed by all attack samples. Machine learning algorithms can be sensitive to the order of training data, so we shuffle the combined dataset to ensure random distribution. So the final result is a perfectly balanced dataset with equal numbers of normal and attack samples, which will train a more effective and unbiased classifier. So the next step is process samples through pipeline after the balanced dataset. Let's see how this function works. This is where actually the most important process happens. So each sample goes through our complete machine learning pipeline. So the process starts with the preprocessor transform single, which converts raw network traffic data into numerical vectors that our neural networks can understand. So this handles all the categorical encoding and numerical scaling we configured earlier. So when feature selection is enabled, each preprocessed sample enters the autoencoder, which attempts to compress and reconstruct it. The reconstruction error, so is the difference between the original and reconstructed values, is the key inside here. So features that are to reconstruct, high error actually, are often more informative for detecting anomalies like attacks. So the ORC selector collects these reconstruction errors and gradually builds a ranking of feature important. There is a critical detail in the autoencoder training. Notice the condition y is equal to 0. That actually ensures we only train on normal traffic. This is fundamental to anomaly detection. The autoencoder must learn what normal looks like, okay? Not what attacks look like. If we train it in normal data, it will learn to reconstruct attacks well, defeating the purpose of anomaly detection. So the progress reporting shows preprocessing speed and number of selected feature. That actually change dynamically as the ORC selector learns. So by the end of these steps, actually we have processed samples with reduced feature sets ready for classifier training. Next step is a train classifier. It actually begins with a crucial step is finalizing our feature selection, okay? Through how the pipeline preprocessing, the ORC selector was continuously updating its feature rankings as it saw more data. Now we call force recompute to get the final definitive ranking based on all the data we have processed. So actually, this ensures our final model uses the most informative features. So during pipeline processing, different samples might have been processed with slightly different feature selections as the ORC selector was still learning. So now we reprocess all the samples with a final locked feature set to ensure that every sample uses exactly the same feature. So this consistency is crucial for a reliable classifier training. So the actual training happens with the self-ref fit, where our SGD classifier learns to distinguish between normal and attack traffic. Actually, the SGD classifier is particularly well suited for this task because it supports incremental learning. That is what we are going to see later. Now we are just discovering the batch training we just train once at the beginning, but later with the incremental learning we will see why we choose this approach. So it can update actually its knowledge as new data arrives without forgetting what it learned before. So the timing information helps us to understand how long training takes and which is useful for capacity planning. The next step is calculate optimal threshold. Is actually fine-tuning a security system sensitivity. So by default, most classifiers use just 50-50, 0.5 as the decision threshold. If the attack probability is above 0.5, classify that as attack, otherwise classify as normal. But this arbitrary threshold rarely gives the best real-world performance. So the code uses precision recall analysis to find the optimal threshold. So instead of processing all training data, which could be slow, it intelligently samples 10,000 representative examples while maintaining class balance. For each threshold value, it calculates precision, so how often our attack predictions are correct, and recall how many actual attacks we catch. Then finds the threshold that maximizes F1 score, so it's the harmonic mean of precision and recall. So the stratified sampling approach ensures we test our threshold on a balanced mix of normal and attack traffic. This method, the precision recall curve, actually that tests many different threshold values and shows us the trade-offs actually. A lower threshold catches more attacks but generates more false alarms, while a higher threshold reduces false alarm but might miss some attacks. So the optimal threshold gives us the best balance between these competing objectives, so which we then save in our classify configuration for prediction use. So the next step in the execute training is, after calculate optimal threshold, is this part. Actually, the production threshold adjustment represents the difference between laboratory conditions and real-world deployment. So while our optimal threshold maximizes F1 score, as we saw, production environments often maybe they have different priorities, and in many organizations maybe false positive incorrectly flagging normal traffic as attacks can be more costly than false negatives because they trigger unnecessary investigation alerts. So by adding in our case 0.2, we are making just the system more conservative, but this is a parameter that you can modify depending on your need. The next step is save models and metadata. We save all the trained model actually in this function directly to artifacts folder. We save here for later use. We create a human readable feature list for interpretability. Save comprehensive metadata, including training statistics and configuration. So actually ensure all information needed for incremental training and prediction is preserved. And at the end, we print a training summary, as you see here, that provide actually a comprehensive summary of training result. So let's start our training. We are already in our virtual environment. Here we go. So we have a lot of logs here. When the script starts, actually all this configuration summary that tells you exactly what's about to happen. So the system validates that your data file exists. In this case, the UNSW training data set with over 175,000 rows. This validation step actually is crucial, as we saw, because it prevents you from starting potentially an hours-long training process only to discover a missing file. We have actually all this information about numerical feature, categorical features, potential label columns, and samples data. So actually the data analysis phase is where the system become actually smart about discovering the features. So look at how it automatically discovered 30 numerical features and 13 categorical features from the 45 columns. It even suggests which column should be your label. It detected both at the cat and label, but we are using the binary label column for our classification. Here, actually, this is actually the part where there is the smart preprocessing that 12 features actually need log transformation because they have extreme ranges like as load ranging from 0 to over 4 billion. So the system says, I'm going to log transform as bytes because it has a range of 12 million. So this prevents features with huge values from dominating the machine process. So the robust incremental scaler is particularly clever because it uses median and interquartile range instead of mean and standard deviation. So making actually resistant to outliers. So this is perfect actually for network traffic data where you might have occasional extreme values. And we have also the model architecture confirmation with all the parameters. The logs actually confirm our model architecture, a 42-dimensional input going into a 32-dimensional autoencoder bottleneck. Then the ORC selector will choose the top 30 most informative features. Notice it says batch mode, no locking. This means that the feature selector will process all training data before making final decisions, unlike incremental mode that we will see later, where features get logged after seeing enough samples. So in the incremental training, we don't have a batch data, we have just data on the fly coming from the stream, but we use the data only for training. It means that in the very first steps, we need to select the features first, lock them, and then we use all the future samples only for training the classifier. So we train the autoencoder first, we select the feature first, and then all the future data is just for training and improve the classifier. And finally, you see the data loading process. 100,000 is every 20,000 samples. So it means that the system can handle dataset larger than your available memory. Actually, what I love about these logs is how they tell a sort of story from validating your setup, understanding your data, making intelligent preprocessing decision, show you real-time progress. So this is just a black box running machine learning. It's a transparent system that explains every decision. So here is where we see the power of the intelligent dataset balancing. The original data had a significant imbalance and 74,400 normal samples, but 131,000 attack samples. So the system automatically undersamples to create the perfect balance, 74,400 samples for each class, reducing the total from 206,000 to 148,000 samples. So this is 1-to-1 ratio, prevents the model from being biased toward the majority class. And pipeline processing here, we can see actually that shows the steady progress at around 400 to 450 samples per second, with the ORC feature selector consistently identifying 30 features as the most informative. And then we get into the testing phase that actually reveals the true performance of our system, testing on 10,000 randomly sampled example from 51,000 available test samples. So maintaining the natural distribution of 46% normal and 63% attacks. We see that consistent performance throughout. So F1 score around 82% and accuracy around 80%. Here, precision 94%, recall 73%. Actually, it's not the best metrics of the world, but are pretty good for this specific case. The precision of 94% actually means that when it flags an attack, it's correct 94% of the time, crucial for minimizing false alarms, and the recall of 73% means it catches about 3 out of 4 attacks, which is solid for a production system. Looking at the confusion metrics here, we can see that 3,387 true negatives correctly identified normal traffic, and 4,629 true positives correctly identify attacks. And we have 273 false positives that actually are normal traffic incorrectly flagged, and 1,711 false negatives missed attacks. So this performance demonstrates the effectiveness of our multi-stage approach. And yeah, let's go to the next step, and now we're going to discover how the incremental training works. So now we will see how the incremental training works. It makes the system to continuously learn from new data without forgetting previously learned patterns. So this is crucial, for example, for real-time adaptation. Learning from streaming network traffic is also memory efficient because no need to store or retrain on historical data. And is also a sort of a continuous improvement. Model gets better over time with more data. Maybe the normal traffic change over the time, or also we need to train different attack types. And also for a production deployment, it updates model while serving predictions. So the server at one side with the ML service receives data from the application server, from the application monitoring service, and trains continuously as packets arrive. We decide what kind of data to send, whether it's normal traffic with label 0 or attack traffic with label 1. To train for attack traffic, we need to simulate real attack traffic, okay? And for this, we create a special script that we will see later. So the entry point is in ML AC2 service. The endpoint is train here. The incremental training is triggered through this Flask web service that receives streaming data via HTTP post request, but you can also apply HTTPS, of course, if you apply certificate. So the first step is the Flask initialization, and we import all the required libraries, especially the incremental trainer from our incremental training module. So this will be actually the bridge between the web service and our ML pipeline. The global variables, maybe for someone might seem unusual if you are used to object-oriented programming, but they are practical for a web service. So the Flask application needs to maintain model instances across multiple HTTP requests, and global variables ensure that our trained models stay loaded in memory between requests. The incremental trainer variable will become our main interface for updating models with the streaming. So when we start the application, apply the initialize incremental trainer. Let's see this function. So the function create the incremental trainer instance pointing to the artifacts directory. This is where all our trained models are stored. The initialize or load models call checks whether trained models already exist from the training. If they do, it loads them into memory ready for incremental updates. If not, it just prepares to initialize new models from the first batch of streaming data. So it checks if we have something already created for the batch training or from previous incremental training. If not, we just initialize the model. So this flexibility allows the system to work whether you are starting fresh or building on existing models. And we have also a production ready error handling with different log levels. After this, let's see the train streaming that actually is our endpoint. This endpoint actually is the heart of our streaming machine learning system. When external systems want to send new network traffic data for training, they make HTTP post request to this endpoint. The function begins with careful input validation. It checks that the request contains JSON data with a flows field containing the actual network traffic samples. This validation is important because malformed requests could crash our system or corrupt our models. If validation fails, we return clear error message with HTTP status code 400. once we have valid data, the function delegates the actual machine learning work to our incremental trainer. So let's discover the incremental trainer class. We go to incremental train py. We find the class here. In the init part, actually set up the incremental trainer with proper configuration, initialize placeholders, set up counters for tracking training progress, and handles configuration loading with appropriate defaults. The method initialize or load models checks if the train model already exists from batch training. If model exists, it loads them from incremental updates. If no model exists, you prepare to initialize them from the first streaming batch. And the load existing models is here. And as it loads all the train model from the artifacts directory. Restore training statistics and class distribution counter, so handles feature selection state, synchronizes classifier state with metadata, and assures backward compatibility with older model version. We see the process streaming batch. Actually, we invoked from the Flex endpoint. Actually, processing a streaming batch is where incremental training comes to life. Unlike a batch training that processes all data at once, this method handles small batches of real-time network traffic data. So the process begins by extracting features and labels, okay, from the incoming flow data, converting the JSON structure into the format for our ML pipeline expect. The method handles a crucial scenario. What if this is very first batch and we don't have any train model yet? So the code checks if self-processor is known at this line and initializes all models from scratch if needed. So the preprocessor update step is particularly important for production systems. So real network traffic might contain new categorical values that weren't seen during initial training. New protocols, new IP address ranges, new port numbers. So the update with new data is extremely important. It teaches our preprocessor about these new categories, while partial fit scaler updates our numerical scaling based on the new data distribution. So the two phases training approach is sophisticated because during phase one, the ORC feature selector is still learning which feature are most important. So we avoid training the classifier of unstable feature sets. So as you can see here, if phase one is feature selection stabilization, don't train the classifier yet. Phase two, stable classifier training after features are locked. If the ORC selection is locked, we have enough data to select the features, we go to the phase two. So if it's locked, we fit the trainer, okay? And if it's not locked, we keep training the autoencoder and the ORC. So we go to the save update models. Actually, this function save all updated model components to disk. It updates training metadata with current statistics, preserves, for example, feature selection state and lock information, and ensures the model are always saved after successful batch processing. And it also, of course, maintains backward compatibility with batch trained models. Now I want to guide you through what happens under the hood when new batch flows arrive from streaming data and show you step by step what occurs in the workflow by analyzing together every single line of code. So we are in the process streaming batch. So we receive from the Flask a new flows data, a new batch of data. And the first important function that we get is the update with new data. Okay, we already saw this first part where it elaborates actually keys in the dictionary and check the features and it transform in data frame. But let's see what happens when we use this data to interact with existing model. Let's analyze update with new data. We go to the data processing with the instance preprocessor that we already initialized. Okay, this is the function. Actually, these methods handles critical challenge of streaming data. It's like an answer to the question, what if we see a new category we've never seen before? Okay, we have as input, okay, a data frame with new data, and the output is going to be the dictionary describing what changed, the update info. Okay, so let's see line by line. We start from here. Actually, this condition ensures that preprocessor was trained initially, so it prevents calling update on untrained preprocessor, and it throws a clear error if violated. It initializes the info dictionary. We have this new category found, that is a Boolean, dimension change, update encoder. So it detailed actually info about each categorical feature that changed and list of encoder names that got updated. So we entered this loop that actually iterate through each categorical column. For example, we have a protocol type, service, flag LAN, login, we have different column. The next line actually it check, okay, if the column exists, okay, it get the current categories in the encoder. Example, if we have a protocol type column, it get the current categories like TCP, UDP, and others. And these are all categories the encoder knows from train, okay? If we go to the next line, it get the new categories in the streaming data. So df call, get the column data, okay? Drop an A, remove any not a number or null values. Yes type, convert to strings that ensures consistent type. And then we have a set that get unique values, and also minus current categories that set the difference to find the new ones. So if any new category exists, okay, it enter the next block. And first of all, update info, that's a global flag, true, we found something new, and add columns named to list of updated encoders. Okay. So we go to the next line. Actually, in this part, it prepare all categories. Okay, convert set to list. In this case, it convert new to list. Okay, convert the new to list, and then it generate all. At this point, it creates fresh label encoder instance. It fit it with all categories, old plus new, and the result is like maps all four categories to integers. So we create like a new encoding map, and then we go to the next block, actually create a detailed change record. And at this point, replace the old encoder with the new one. So the future transfer will handle the new category correctly. It returns the complete change summary. Let's discover the partial fit scaler. The partial fit scaler that actually we get at this point from the incremental training after the update with new data. If the feature is not known and the feature df is bigger than 0, we're going to invoke this partial fit scaler. It check if we have a numerical feature and if the scaler was initialized. So if n is false, method does nothing, so return silently. And the next line, it check the feature list. This line ensures that the numerical feature list isn't empty. And then at the end, it performed the partial fit. The upper route decorator tells Flash to call this function, as we know. After this, we have a try-catch section. It receives the incoming network data and logs the request. So the data comes in JSON format containing various network metrics. After this, we have a section that ensures that all ML models are loaded and ready before attempting any predictions. If models aren't available, the service returns an HTTP 500 error. And then we go to this part where we extract the individual ML components from the incremental trainer. So each model has a specific role in the prediction pipeline, as we saw before. In this section, actually, it determines whether to use a feature selection based on how the models were trained. So after this, we get X processed, that actually the preprocessor transform raw network data into a format suitable for ML models using the data preprocessing as we saw before. So this included normalization with a robust scalar, encoding and feature engineering with the autoencoder and ORC system. And after this, when with the feature selection is enabled, this pipeline uses, as we saw, an autoencoder to detect anomalies and ORC to identify the most important feature for classification. But if we don't switch on the apply feature selection, all the preprocessed features are passed directly to the classifier without filtering. After this, we go to the SGD classifier that makes the final prediction that we can find here, providing both a binary decision and a confidence score. So we prepare the response. Of course, we label the prediction 1 or 0 depending on the optimized attack threshold that we calculate during the training. Just a note, something to know about that if they use the best training, the attack threshold is calculated dynamically, okay, to maximize the F1 score. But if we use the incremental, if they use the incremental training, we cannot calculate dynamically because we don't have all the data together. So we need to decide which value we want to use. Normally 0.5. So the final section packages all the prediction information into a comprehensive response that include decision, confidence, and metadata. We have also some logging and also error handling, and we return the string from the result. So now we are on the server hosting the application we need to monitor, along with the agent responsible for capturing network packets and creating data flows to send to the ML service we just explored for prediction or training. As you can see, this repository contains several folders. All of these are components of a Next.js application, but you can monitor any kind of application and use any frameworks that you want, of course. In this case, is my portfolio website. So the network agent folder here is where you will find the network monitor agent script, and that includes the packet sniffer and handles the creation of a structured data flows for both training and prediction purposes. Before explaining the script, let's look together at the list of extracted metrics features and the meaning of each one. So the following metrics are extracted from network flows and sent to the ML service for training or prediction. So think of these metrics as the vital signs of network traffic that help identify normal behavior versus potential attacks. So we have basic flow metrics. The first is the duration, as the total time span of a network conversation in seconds from where the first packet is sent until the last packet is received. Actually, it's important because as short duration flows with high packet counts might indicate scanning attacks, while unusually long flows could suggest data exfiltration. We have total packets, so it's the complete count of all data packets exchanged in both directions during the conversation. Abnormally high packets count in a short time can indicate DDoS attacks or port scanning activities. We have forward packets. It's a number of packets traveling from the client attacker to your server. And it matters because a high forward packet count with low reverse packets might indicate a one-way attack like SYN flooding. We have reverse packets, so it's the number of packets sent back from your server to the client. So the ratio between forward and reverse packets helps identify the type of communication pattern. And then we have the total bytes, the total amount of data transfer in the flow, counting every byte in every packet. So unusually large byte transfer might indicate data theft, while tiny byte counts with many packets could suggest reconnaissance. We have forward bytes, the total amount of data sent from the client to your server. So large forward byte might indicate someone uploading malware or attempting buffer overflow attacks. The reverse byte on the other side is the total amount of data sent from your server back to the client. It matters because unexpectedly large reverse byte could indicate a successful data exfiltration or information leakage. And then we have the packet size statistics group. First of all, we have the min packet size. This is the size of the smallest packet in the entire flow. And many attack tools use a fixed minimum packet sizes. Unusual minimums can be attack signature. We have max packet size, is the size of the largest packet in the flow. We also have the average packet size. The average size of all packets in the flow is the total bytes divided by the total packets. So normal web traffic has predictable average sizes. Deviations might indicate malicious activities. We have the forward average packet size. As the name suggests, is the average size of the packet sent from client to server. And attack traffic often has different packet size patterns that legitimate the request. We have a reverse average packet size that actually helps to identify if the server is responding normally or sending unusual amounts of data. We have timing features, packets per second, the rate at which packets are transmitted, total packets divided by the duration actually, is extremely high rate can indicate automated attacks or scanning tools. We have byte per second, the data transmission rate throughout the flow. Bandwidth consumption pattern help distinguish between normal usage or flooding attacks. We have forward packet per second, the rate of packets coming from the client or attacker. High forward rates with low reverse rate often indicate denial of service attempts. We have the reverse packet per second, is the rate of packets being sent by your server. Unusual server response rate might indicate it's being overwhelmed or exploited. We have the TCP specific features. Actually, we have the TCP flex count, the variety of different TCP control flags seen in the flow. So normal connection use a predictable flag combination. Unusual patterns indicate attacks. We have SYN count of synchronized flag, which initiate new connections. Multiple SYN flags without proper responses indicate SYN flood attacks. We have a fin count, the count on finish flag, which gracefully close connections. So proper connection termination patterns differ between normal traffic and attacks. We have RST count. Actually, it's the count of RST of reset flags, which abruptly terminate connections. RST counts often indicate port scanning or failed attack attempts. We have the hack count, is the count of acknowledgement flags confirming data received. Hack pattern help identify the health and legitimacy of TCP connection. We have the forward TCP flags, is the variety of TCP flags used by the client in their packets. Attack tools often use unusual flag combination not seen in normal traffic. The reverse are the same way. Variety of TCP flags used by the server response packet. We have the IP level features. We have the SRC port, the port number used by the client source. Certain attacks originate from specific port ranges. Unusual source ports can be suspicious. So we have DST port, the port number on your server being assessed is 80 for HTTP, 443 for HTTPS. And it matters because actually attacks often target specific services. Unusual destination ports might indicate scanning. We have protocol, the IP protocol number 6 for TCP, 17 for UDP, 1 for ISMP. It matters because different protocols have different security implications. Some attacks use specific protocols. We have forward TTL, is the time to leave value from client packets, how many network hops the packets can make. So TTL values can reveal the attacker's operating system and detect spoofed IP addresses. Reverse TTL, time to leave value from server response packets. We have the TCP window size forward, is the amount of data the client can receive before acknowledgement is needed. Window size patterns can actually identify the client's OS and detect certain attack tools. We have the TCP window size reverse, is the amount of data the server can send before needing acknowledgement. Server window size can indicate congestion or attempts to slow down connections. And we have the flow state features. So if it's bidirectional, a binary flag, 1 or 0, indicating whether packets flowed in both directions. One-way flows often seems like attacks, like a UDP flows, while bidirectional flows are usually legitimate. We have the connection state and the final state of the connection, con for establish, fin for properly close, int for interrupt. Attack traffic often has abnormal connection states compared to legitimate traffic pattern. So these 29 metrics work together like a puzzle, while Any single matrix might seem normal. The ML model looks at all of them together to detect patterns that humans might miss. Okay, let's go back to the network monitor class from the script. So the network monitor agent actually is a script that acts as a security guard for your web server. It monitors all network traffic flowing to and from your server, analyzes pattern in this traffic, create flows, and send to the ML service to train or prediction. Some characteristics about the flow. Data on the internet travels in small chunks called packets. Each packet is like an envelope with an address IP, a port number, and the actual data inside. Our agent uses a tool called SGD to intercept and read these packets. The agent doesn't decide on its own as if the traffic is malicious. It uses the external MLS service. The network conversations are two-way streets. When you visit a website, packets flow from your browser to the server and from the server back to you in reverse. So the agent tracks both directions, uses a 5-tuple classification: the source IP, destination IP, source port, destination port, and protocol. Let's see how it works together. There is an initialization phase. The processing is parallel because we are processing in parallel the packet capture thread that continuously captures packets from the network. The flow processing thread actually groups packets into flows and extract features, and training thread is the training mode only that we will see just in a few minutes. That sends batches to the ML service. So let's discover the flow lifecycle. It's composed by 5 steps. Okay, first steps, the packets are captured and queued. Second steps, the related packets are grouped into bidirectional flows. Third step, the flows complete after timeout or idle period or TCP termination. Fourth, the features are extracted from completed flows. And fifth, the features are sent for prediction or added to training batches. So the integration can be in prediction mode or training mode. Okay, let's start to analyze the code. When the network monitor class is instantiated, it sets up all the necessary configuration and prepare the agent for monitoring. So we store the configuration dictionary. It get the network interface to monitor at the ATH0 or the VLAN 0. Think of this choosing which network card to listen on. And we have the mode. So the operating mode can be train or predict. We have the batch size for training mode, how many flows to collect before sending to MLS service, like filling a basket before taking it to process. We have the label for training. 0 means normal traffic, 1 means attack traffic. We have the base URL is the URL for the ML service endpoints. We have the predict endpoint is actually the endpoint for attack prediction. Then point for training. We have the flow timeout, that is how long to wait before considering a flow complete, waiting for a conversation to pause before assuming it's over. The capture window actually is the how often to process collected packets every 5 seconds. The max packets per flow, maximum packets to collect per flow before processing. The packets queue, I create a queue to store capture packet temporarily. Max size is, we put 2000. It means that it can hold up to 2000 packets in memory, but I think it's a little bit small. We can put 10,000. Extract the IP, okay, and then the ML endpoint IP is the extract the IP address of the ML service to exclude it from monitoring, okay? We don't want to monitor our own monitoring traffic, of course, because you will see when we monitor the traffic, we get all the traffic from, for example, the load balancer inside the EC2, other services that are communicating with our EC2 instance. If we are connected with SSH on the port 22, we also get this traffic. So we get actually all kind of traffic. The server IP detects this server IP address, the control flags and counters, like a flag to control when stop monitoring, the counter for processed flows, counter for capture packets. For training mode, we have current batch being filled, queue of batches ready for training. This flag is to prevent concurrent training, for example. We have the temp pcap dir that actually create a temporary directory for any packets capture files. active flows, a dictionary to track active network flows. We have some logging here. And let's see actually the first method. So when we initialize this file, it starts monitoring. This is where the monitoring actually begins. It creates separate trays for different tasks so they can run simultaneously. You can see here the capture trade. Actually start is trade 1 capture packets from network interface. The trade 2 process capture packets into flows. So this runs simultaneously with packet capture. The trade 3 only in training mode process training batches, sends collected flow data to the ML service for training. And at the end, so it keeps the main trade alive. Without this, the program will exit immediately. So let's see the capture packet function. This trade continuously capture packets, as we saw, from the network interface using SGD. We define this function. We extract the IP address from the packet. Packet IP gets the IP address, the IP layer of the packet. Skip the packets without the IP address because we want to know, always want to know the IP address. One is to identify a specific flow, and it's also important for block specific ID if we want to integrate a real-time blocking system for attackers. We don't want actually to create an infinite loop by monitoring our own monitoring, so we skip the ML endpoint traffic. Here we extract the port numbers, different for TCP and UDP. We check if this is a packet, okay, or if we check if it is a TCP packet or a UDP packet. Here we want to skip packets on excluded ports like SSH, DNS, so we can actually set excluded ports if we want to skip some of them. And here only process packets that involve our server, of course. We are only interested in traffic to from our Next.js app in this case. Here we count packets and log progress every 500 packets. And here actually is where we start sniffing packets on the specified interface. The PRN packet handler means call packet handler for each packet. And then stop filter stops actually capture when self-running because false. Let's see also the process flows is the second thread. It takes actually capture packets and groups them into flows that we call network conversation. The window packets actually list to collect packets for the current window. It track the last process time, it track when we last processed the packets. Keep processing while the monitor is running. Here we try to get a packet from the queue. Timeout 1 actually means wait up 1 second for a packet. The packet here add the packets to our current window. And if no packets available in the queue, check if we should process what we have collected so far. We go to should process, actually decide if we should process the window now. Determine why we are processing. And at the end, it processes the collected packet, process packet window here, and clear the window and reset the timers. We go to the next step, that is generate flows from packets. This function actually groups packets into bidirectional flows using 5-tuple classification that I mentioned before. Here we skip if no packets to process. Get the current time for tracking flow activity and process for each packet and assign it to a flow. Okay, so it check if packet has IP layer, extract all the IP information. We have the protocol, each protocol has a number. Here is skip, as we saw before, the melting points traffic, that is important. We initialize, because if not, we're going to create a sort of loop. That here initialize ports to 0. Extract port numbers for TCP packets, extract port numbers for UDP packets. We skip excluded ports as we saw before. So in this part, we create a bidirectional flow K. We normalize the K, so the packets in both directions map to the same flow. So this packet is in the forward direction, and this packet is in the reverse direction. So this swap SRC DST to create the consistent key. And then we create a new flow if it doesn't exist. Okay. In the flow data, we get the flow data, of course, and we determine actual packet direction. So this is actually complex because we normalize the flow. Okay. But then after this, we add the packet to the appropriate direction list. And then at the end, we update the flow timing metadata. Now, at this point, we check which flows are complete and should be processed. We calculate the flow, age, and idle time. We determine if flow is complete here. We process all the complete flows in this part. And at the end, we just log informations. Let's go to the next step, that is process completed flow. When a flow, in this case, is complete, we process it and extract features for ML analysis. So we get the flows endpoint. We only process flows that involves our server. Skip very short flows, less than 2 packets. This doesn't have enough data for meaningful analysis. Increment flow counter. Determine which IP is the remote client and the direction of the initial connection. We log the flow for debugging here. We are going to extract all the feature. So this feature actually will be sent to the ML model. And here we decide, depending on the mode. So if it's predict, we send the feature to ML model for attack prediction. If it's train, we add feature to training batch with the label. Let's see the function extract SGD feature here. We can find here that actually is crucial method because it extracts numerical feature from network flows that the ML model can understand. We get the packets from both direction. We handle empty flows. We calculate flow duration in seconds. Here we count the packets and bytes in each direction. We calculate total bytes for summing packet lengths. Here we have the total packets in the flow. So we sum the forward and reverse. We initialize the features, and here we're going to assign the matrix, the name, and the key, and the values that we already calculated. Here we have a packet size statistics. We get the size of each packet. We calculate the average packet size for forward direction and the average packet size for reverse direction. We have all the timing feature here, rates per second. We have the TCP flag analysis. TCP flags help actually to identify the type of connection and potential attacks. Under this, we are going to count specific TCP flags, like a SYN for connection initiation, FIN for connection termination, connection reset, and acknowledgement. And after this, we're going to store the port and the protocol feature. Here we have the time to live feature that helps to identify operating system and detect spoofing. Actually, we get the TTL from the first packet in each direction. Okay. We have the TCP window size, indicates the congestion and connection quality. And also we have the flow state feature. So we are determining if the flow is bidirectional or not. We have also the connection state and get it here. And then we can see the send for prediction. That is just when it's prediction mode, this method sends extracted feature to the ML service. As you can see here, it creates a clean feature set with only the feature that the model expects that we define. We create a detailed log entry for debugging. And then we send the HTTP post request to the ML service. We analyze the response of if it's successful, if it's 200. We parse the response and then we get the attack probability, the prediction, and we log what we get from the answer. But if we are in training mode, we use this method, this function. The agent collects flows in batches and sends them for model training. So it creates a clean feature set as the same way. It adds the flow to the training batch with metadata and log what type of traffic we are collecting, if it's label 0 or label 1. Actually, we have to set this label when we want to train the model. We set the label first. We check if the batch is full. If it's full, actually, add completed batch to training queue. And actually, it's a list. Create a copy so we don't modify the original. And at the end, it clear the current batch to start collecting new flows. We have process training queue, actually another function that process the training batches sequentially. We keep processing while the monitor is running. We try to get the batch from the queue. Here, timeout 5 minutes, wait up to 5 seconds for a batch. And then here we send the batch to the ML service for training. Here we mark the queue task as done. And if the queue is empty, no batches to processor. Right now it continues. We have the send training batch to ML that we see just right now. Actually send a training batch to the ML model for training. It creates the payload. It sends to the ML training endpoint here. The timeout, we set everything. All this is orchestrated by the main function that is here. It starts the monitor, as we saw. It gets the default interface. It's a helper function to automatically detect the network interface here. This is the configuration dictionary. This is where all settings are defined. And we have the base URL for our ML service, interface, the mode, if train or predict, flow timeout, capture windows, seconds between processing windows, max packet per flow, max packet before processing actually, is flows per training batch. So batch size is the number of flows per training batch. And label, as we know, 0 is normal traffic, 1 is attack. So now comes the exciting part. So we are about to deploy our entire sophisticated network attack prediction system with just a few clicks using the power of AWS CloudFormation infrastructure as code. So we will transform a single YAML template into a complete production-ready infrastructure that will normally take hours to set up manually. Think of this as a one-click deploy moment where all our work comes together. In the next few minutes, AWS will automatically create load balancer with the SSL certificates, auto-scaling web servers, ML prediction services, complete CI/CD pipeline, security groups, networking and monitoring login system, and many other components. So all orchestrated perfectly by CloudFormation infrastructure as code. Is really magic. Let's think about some key benefits. First of all, you can repeat it in just few clicks. So deploy the same infrastructure multiple times. You can track infrastructure changes in Git. No manual intervention. Automatic rollback on failures. CloudFormation also handles resource dependencies automatically. And many other benefits. Let's look at our template structure. Actually, it creates a load balance web application, auto-scaling group, 2 complete CI/CD pipelines, that one for the ML service, another for the app with the monitoring agent, both using GitHub integration via CodeStar connection. So I will show you how to just trigger a new pipeline just with a push on GitHub. And it's going to be all automatic. It also creates policies, security configuration, health checks and monitoring, and many other stuff. Let's deep dive inside the template structure. The section 1 is specify the CloudFormation template format version, and this is just a human readable description of what the stack creates. The next section is parameters. The parameters are like variables that users can input when creating the stack. They make templates reusable across different environments. We can specify, for example, the VPC to deploy, the public subnet for the load balancer, for example, the security group for traffic control, certificate, the keeper name to get into the EC2 instances, the instance type, both instance type, one for the EC2 that have the EC2 with the application, the other one for the ML instance. For the ML services, we are going to use the T3A medium in both cases. The root volume size, 36 GB for both servers. The startup AMI, that is just a boilerplate for Ubuntu with 22.0. The CodeStar connection ARN with the connection and GitHub app integration. Information about the repository where to download the code. That actually is my GitHub. The branch name, the code pipeline manage policy ARN. We also have to attach some policy for the service, and also the build spec file name. I will show you later the function of this. Actually, it is in code pipeline. And using parameter default makes testing easier also while still allowing customization. Let's go to the heart of CloudFormation, that is the resources part. So now we dive into this section, which is where all the magic happens. This is where CloudFormation creates every single piece of our infrastructure. So part A, the application load balancer, which is the entry point for all the web traffic coming to our system. When we declare load balance as a resource, we are telling CloudFormation to create an AWS Elastic Load Balancer. In this case, is version 2 load balancer. That's what the type specification means. So the sub function actually is here is substituting our stack name into the balancer name. So if your stack is called production, your load balancer will name the production balancer. The scheme being set to internet facing means this load balance is publicly accessible from the internet. It's what your user will connect to. So this load balancer distributes incoming HTTPS and HTTP requests across multiple EC2 instances, providing availability and fault tolerance. It handles also SSL termination using ACM certificates and enables auto-scaling by routing traffic only to healthy instances. We have configured it to span multiple availability zones and enable HTTP2 for better performance. So load balancing cross-zone enable actually ensure traffic is distributed evenly across availability zone, and client keep alive seconds determines how long connections stay alive. After this, we have the target group configuration, which define which EC2 instances will receive traffic from the load balancer. Think of it as a collection of instances that the load balancer can route or request to. So the target group perform health checks on the API health check endpoint that I create in my Next.js application. It's just a 200.0.0 response. And after 5 consecutive successful health checks, an instance is marked as healthy and starts receiving traffic and will be managed inside the auto-scaling group. If we get 2 consecutive failure here, the instance is marked unhealthy and removed from rotation automatically. So this ensures that only healthy instances receive traffic from your users. So the target group also manages sticky sessions. When stickiness is enabled, it will route the users to the same instance for their entire session. That's quite important because maybe the application works with the cookies and the browser the backend must be always aligned with the front end, with the client, with the browser, which is useful for stateful application. The part C is the listener HTTPS. Actually, we configure how the load balancer handles incoming connection with our listeners. We create 2 listeners, that is HTTPS, HTTP. One for the HTTPS actually is on port 443, and one for HTTPS is on port 80. This is the standard. So HTTPS listener handles secure traffic using the SSL certificate we specified in our parameters. The HTTP listener has a special job. It just redirects all HTTP traffic to the HTTPS, enforcing security by ensuring all communication is encrypted. This means, for example, if someone arrives in HTTP yourdomain.com, they will automatically be redirected to HTTPS yourdomain.com. So it's a security best practice that protects your user data. Next, we have the launch template. It's like a blueprint for every EC2 instances that gets created in our auto-scaling group. It defines the AMI to use, the instance type, the security groups, and most importantly, the user data script, that runs when each instance starts up. This user data script is crucial. It updates the Ubuntu packages. It starts, for example, the AWS code deploy agent that is necessary for our deployments to use the code pipeline. It configures the agent settings and enables it to auto start on boot. It also sets up cleanup script to maintain only the latest deployment and logs everything to the specific user data log for troubleshooting. So after this, we define, so this is the script, the user data script. After this, we define the auto-scaling group. That is a wonderful service provided by AWS. It manages a fleet of EC2 instances that can grow or shrink based on demand. We have configured it to maintain a minimum of 1 instance, and so our application is always available. Scale up to a maximum of 3 instances to control costs and start with a desired capacity of 1 instance. The group automatically replaces unhealthy instances and distribute instances across multiple availability zones for high availability. So the scaling decisions are controlled by our scaling policies. We have a scale-up policy that adds instances when CPU utilization exceeds 80%, that is the target value here, and a scale-down policy that removes instances when CPU drops below 80%. So this target tracking approach maintains optimal performance while reducing cost. Next part is the ML pipeline. We have here the ML instance. So for our machine learning workloads, we take a different approach. Instead of auto-scaling the auto-scaling we apply only to the server with the web app application with the agent, with the monitoring agent. But for the ML instance, our machine learning prediction service, and we operate independently from the web application scaling. We don't need the scaling at this moment, so we associate it just with a fixed IP address here, an elastic IP that is we specify here, which provide, I already create this, is already my AWS account, but if you want to create on the fly directly, if you want to make it automatically, you can anyway integrate the creation here and actually provide a consistent endpoint for our ML services. The IP association resource ensures that this IP stays attached even if the instance restart. If you don't apply the elastic IP, every time you restart the instance, it changes the IP. So here we define the ML instance at the same way with all the user data to activate our ML services. And after the CI/CD pipeline, we start with the S3 bucket, okay, that stores all our pipeline artifacts. This bucket is essential for our pipeline operation. It stores source code archives from GitHub and all build artifacts as they move between the source, build, and deploy stages. So the next part is the EC2 role. So now let's talk about the IAM roles, which are critical for security. We create 4 different IAM roles in our template. The code pipeline service role gives permissions to orchestrate our entire deployment process. So the code build service role allows code build to access source code, and we find here directly in the parameters. And the code deploy service role permits code deploy to deploy application to our EC2 instances. And finally, the EC2 role is what our instances use to communicate with the AWS service. And we find here. And after this, we have the code build project here. Actually, our code build project are managed build services that compile and package our application. In our case, using Next.js is going to run the famous npm build in a different machine, and it create the build and it store as an artifact to deploy later to the real final production machine. So we create 2 code build projects, one for the main web application that reads, we will see later, this file that is build spec dual ASG YAML. I will explain what is the purpose of this file. And it uses actually an Amazon Linux 2 container with a build generally small compute type, so which is cost effective for most build workloads. And code build automatically provisions the build environment, runs our build commands, and outputs the artifact to our S3 bucket. The next part is the code deployment group. It handles actually the deployment of our application to EC2 instances. We create code deploy application for both our web app and ML services, which define the deployment platform as EC2. So the deployment groups specify which instances receive deployments. The web app group targets our auto-scaling group instances, while the ML group targets the single ML instance. So we are using as an in-place deployment strategy, which means we update existing instances rather than creating new ones. This is simpler and more cost-effective than blue-green deployments, but that's depend on your needs. The without traffic control option means that we deploy directly without load balancer integration. We also create a custom deployment configuration that limits us to maintaining a single revision, which helps control storage cost. After this, we have the code pipeline resource, which actually orchestrates the entire CI/CD workflow. We create, as I said, 2 pipelines using the new V2 pipeline type. The main pipeline has 3 stages. It has the source stage, which pulls code from your GitHub repository using code star connections. We have the build stage, which runs the code build project to compile and package your application, and deploy, which uses code deploy to update your EC2 instances. The ML pipeline is simpler with just source and deploy stages. We're skipping the build step since ML models often don't need compilation like a Next.js application in our case. So the V2 pipeline type gives us Git-based triggers instead of pulling, which means the pipelines. That's fantastic because it starts immediately when you push code on a specific branch. So the next section is the ML pipeline. We can find it here. That's simpler, no build stage, direct, as you see here, there is a source and direct the deploy. Separate GitHub repository is another repository, and independent deployment cycle. We have the ML pipeline here. And yeah, and at the end we have the output, all the outputs here. So what are the outputs? Actually are just values exported after stack creation, can be referenced by other stacks, and they are useful for connecting resources. The key outputs are like load balanced DNS for assessing the application, resource ARN, pipeline names for monitoring, and actually what you need to output after the stack is created. So let's create our infrastructure with CloudFormation. So I get into my AWS account in Milan region. We go to CloudFormation here. I have a previous stack that is deleting now. Let's create the new one. We create with new resources. We choose an existing template from a template file that we get from our repository. Here is the YAML that we just explained just a few minutes ago. And we choose this. Okay, next step. We give a name to the stack. Let's call network attack prediction stack, and here we go. So it recognizes all the variables inside. It recognizes, for example, it get all the parameters that we saw on top and everything here. So we go to the next, and we don't set the permission, we just let it automatic. And okay, we confirm this and we start the creation. Here we go, we submit. And now we can see here all the event and the creation in progress. Let's see in detail what happened here. If we refresh, maybe here, if we go to resources, we can see in real time all the resources that they are created from CloudFormation. So already create the code deploy application, the IAM roles, code deploy deployment config, the code deploy application, the deployment group, and actually it's all the resources that you already defined in the YAML file. So we are waiting, it's going to take a couple of minutes. So we create the Elastic Load Balancer, S3 bucket where we can find the pipeline artifacts bucket, the launch template. We refresh. And we can see here all the parameters. We can see the outputs at the end. When finished, we will see all the outputs here, the stack information, the events. We see actually all the resources are still, a lot are still in progress. The process is complete and it's all green, create without any errors here. You can see here, create complete. Let's check if the resources are created directly from the console. We can go to the, let's see, to the EC2 instances. Maybe we see some instance already. Here we go. So I already have this one, but it create now these two instances, one for the application with my website and the monitoring agent. Now this EC2 is empty. It only has it only run the user data initial script. So we need to deploy and to trigger the code pipeline to deploy the application and everything and start. And also the ML service we need to deploy with the other pipeline. But one is ready, one is creating, and it creates as our parameters, the T3A medium. It also attached the security group that we specified, that is launch wizard 1, that has some specific port. It applied elastic IP that I defined. So let's check if it creates also the load balancers. Here we go. We have our NAP balancer, the NAP balancer with the specific listeners and rules, and with the HTTP 443 and the HTTP that redirect on the 443. It applies also the certificate that we defined. It actually is for my domain, thevergolabs.com. And also the auto-scaling groups is created as we define in the YAML. If we go inside, we see that is created, and it also managing the first instance that it already created and is healthy. And let's see the pipeline. We go to the code pipeline. We should find two new pipelines. And here we go. We have two pipelines. Actually, this first pipeline fails, so we need to know why. And actually triggered the first deploy, but we are going to refresh with a new push. Maybe there is something in the code that get an error. Okay, no instances. Actually, maybe was too fast. We're going to push again. And also the stack pipeline with the web application where we have three steps. It already get the source, already build, and is going to deploy it. I want to show you how to trigger from the Git. Then we will see together how it starts, how the pipeline starts over again. Yeah, actually we have everything to test our system. The first thing, I just want to change the DNS. I want to route the traffic from our domain directly to this new load balancer that we create just right now. So we are going to test it because I think at the moment the Virgo Labs doesn't work because it's sending the traffic to this unhealthy instance. Maybe it has some problem, but we're going to redirect to this new pipeline, to this new load balancer. Let's go to Route 53. We get one hosted zone. It's the Virgo Labs. That we just change. We added the A record. We use this alias to route directly to the new stack, to the new load balancer that is this one that we create just right now. That is a dual stack NAP stack balancer. We save it. So if the pipeline complete without any errors, we should see the website working. It's still in progress. Let's wait a couple of minutes so we can test off also our website. So we are waiting. The deploy should finish in a few seconds. Okay, perfect. So it finished the pipeline. It also deployed without any errors. Let's check if we can reach our website. And here we go. So the website works, and also maybe the agent should work inside this server. Let's see. Let's get into the server and see how the network monitoring works and if everything is good. Because we also have to trigger again this other pipeline that got some errors, as we saw before. This pipeline need to push again and see what make it failed. We've already seen how the pipelines automatically started once the infrastructure created with CloudFormation, but we haven't yet explored where the build and deploy script are located. So the crucial components that integrate new code from GitHub and make it operational on our EC2 instances. So these scripts are here in the repository. We have both for the application repository and ML service. For the application, we also have the build spec and all the code deploy script here in this folder. For the ML service, we have only the code deploy scripts. Actually, these scripts are the bridge between your source code and the running production services. So they handle the complex process of transforming raw code into deployed functioning application. As we saw, the code build compiles our source code running this YAML, using this YAML, runs tests and produces deployment artifacts. The code deploy takes those artifacts and deploys them to the EC2 instances, and it runs all these script files, and the code pipeline, as we saw, orchestrate this all. So let's start with the build spec dual ASG, and it has this structure. This file defines how to build, in this case, a Next.js application and prepare it for the production deployment. The phase are install phase here. We have that actually set up a node version 22 and runs an npm CI. And the build phase is the it runs the npm run build to compile the Next.js application. It creates optimized production bundles in the .next directory. And the post-build phase removes all node modules after building. Reinstall only production dependencies to reduce deployment size. So actually this optimization can reduce deployment package by 50 or 70%. This is specific for Next.js. If you have another framework, you are going to adapt it depending on your specific stack. And the artifact section here specified what gets sent to the code deploy. It includes all build files, but it excludes development files like .git, .env, config files, and others, and creates a named artifact with timestamp for tracking here. Okay, so the next part is the code deploy lifecycle script. So let's explore the 6 code deploy script that we can find here in this folder. Actually, they manage the deployment on EC2 instances, so these run in a specific order during deployment. So the first script is the before install, as you can see here. The purpose actually it prepares this EC2 instance by cleaning up any existing deployments and stopping running services. Verify code deploy agent is running, stops existing PM2 processes, stop Nginx web server, stop network monitor agent if running, and remove all the application directly to ensure clean deployment. So this ensure we start with a clean state, preventing conflicts between old and new code. So the next script is install.sh. The purpose actually is it sets all the system level dependencies and configuration needed for the application. As you can see here, it updates system packages and install essential tools like curl, JQ, install Python 3, network monitoring dependencies, install or update Node.js to version 22, install and configures Nginx with custom configuration, and removes default Nginx configuration, and install PM2 globally, and set proper file permission. This is really specific and depend on your application. And then we have after install, okay. Actually, it performs final setup after files are deployed, like including dependency installation, environment configuration, sets file permission for security, create the required directories like logs, temp. For example, it handles the environment file setup, clean npm cache, installs Python 3.11, create a system service for network monitoring, that it's our monitoring agent, and creates deployment marker file for tracking. You can see everything here in the file, and this is the systemd service for our agent. And then we have the stop app that gracefully stops all application service during deployment update. We also have at the end start app that starts all application services and configures automatic restart on reboot. And at the end, we also, if you need, you can integrate also some validation. In this case, it validates PM2 processes, check Nginx status, test health check endpoint, verifies network monitoring agent operation. That is really important for our system. Provide detailed troubleshooting information if validation fails, and it return also pace or fail status to code deploy. So let's trigger a new deploy. For example, we make some change to our web application, or also we make some change to our network agent. For example, we want to start, for example, to train our ML service. So we don't want to predict, but we want to train. We are going to change this. We train from zero. We train from scratch using the incremental stream. So we set train, and we're going to train only at the beginning for normal traffic 0. Okay, later we will train, for example, attack traffic. Let's deploy. So we just commit something like deploy for train, and we commit this, and we push directly to our GitHub. So we will see our pipeline that is starting over again. So we will see, here we go, is in progress, is starting, it get the source, it's downloading the last version from the master, from the branch that we set on the on the template. I think is, in this case, as you can see here, the commit that I just pushed now is chore new, is the latest commit. The first step is successful. So you download the code. Now it's building, is running actually this part, is running this build file. Let's see if we can get some logs inside here. Maybe yes. And here we go. We have all the logs. Running code build, YAML location, the setting HTTP timeout. Okay, here we go. Is installing the Node.js. And this mode is not support. Okay, it's just some warning. We have installed 3 commands, pre-built 3 commands, build 3 commands, and post-build 5 commands. Actually, is like this. So it's correct. Now it's installing, is running Nest.js, is building Nest.js application. As you can see, maybe we cannot see, oh, it's still working because it's not deployed yet. It's just building in different machine. So after build, maybe it will stop. It will see the app stopping. No, maybe not, because we are in auto scaling group, so it's going to be always available. We're waiting for the build to complete. Next.js is generating all the page of my website. Here we go. So Next.js completed, and it's running the command npm CI. We remove all the node modules because already built. Let's go back to the pipeline. Let's see in which step we are. We are still in the build. Here we go. We are entering the deploy step. So the build complete successfully. Let's see the logs in deploy. We go inside this step and we view in code deploy. Let's see. Here we go. This is our deploy, and you can see here this deployment lifecycle is in progress. We can see the events, and the event is exactly, it follows exactly our script that we defined before. The application stop, it download the bundle from the previous step that is code deploy, is code build, it download the artifact before it launch the before install script, application start, and we have the last step, and it's all validated. Here we go. So it's still running. So my website is running smoothly. So I want to deploy again the ML service because we got some error and the pipeline didn't finish correctly. As our monitoring agent now is sending data to actually to an instance that doesn't work at this moment. I expect that when I deploy this ML service, everything is completed and they start to communicate to each other. I'm going to trigger a new deployment, but first I want to delete all the models because I want to deploy something fresh. And when it start to train for the first time, it's going to create a completely new model and start a training from scratch. So we delete all the models and we just push new deploy. Let's see if we don't get error this time. I hope. Commit and we push. Let's see what happened. Here we go. So we go to our pipelines. Okay, so it trigger a new start from the code. So it download the code. Let's see if the deploy it completes successfully. Let's see in code deploy all the events. We see what happened. So let's see the events. Oh, okay, the application stop is succeed. Download button is everything okay. Before install, after install. Actually, we didn't see the script, but they are similar to the other application. They are just different script specific for the ML service. We can see them here. If we go to code deploy script, we see something similar. And they just run our application for the production. You can study the scripts line by line. And here we go. We get after install. Maybe this time we are lucky and start to run. And here we go. It's completing the application start. We have the last step, validate step. Okay, our ML service is ready and it works. So now for our, you see, the both instances are ready. Okay, now we just SSH inside the instance and we see if the training is happening without any problem. And we're going to log all the API response from the ML service. So let's get into this. So I get into the ML service server. It creates everything and it looks like everything is working fine. The project is into the OPT folder. To see the logs, actually, we can just journalctl the ML attack predictor, that is the service, and here we go. Okay, so it's working and it shows us each batch, each batch of data that is training. Okay, so we get this training completed using incremental trainer models, streaming training completed, 10 samples processed. So it's receiving data from our application, and we got, as you see, another batch of 10 samples. And if we go to the artifact, we should see the models. At this point, we are not training the SGD yet, but we are training the autoencoder and the ORC, because as you remember, first we need to complete the feature selection steps, and after we lock them and we start to train also the classifier. So in this step we are training the preprocessor, the autoencoder, and other stuff. Let's get into the application server, so we can see also some API answer from this server. I got into the application server, so it deploy everything smoothly, and we have the network agent that actually is working. And to see the logs of the network agent and see actually the API response from the ML service, we just tail the network monitor log, and here we go. We have exactly the answer for each call, that actually for each batch that is training our ML service. As you can see here, we log all the values for training. So it's just the first flow in the batch. The batch has, as we saw before, 10 samples. So this is just the first flow data, and training batch completed successfully. So everything is work. So now the system is training. Now this agent is training the ML service automatically. So we can live like this. And when we reach, for example, 50,000 records, we can start to train for the label 1. So we can simulate a different type of attack, and we can train for label 1. But now we just can leave it like this, and it's training for normal traffic. Okay, that wraps up our deep dive into building a production-grade ML-powered network attack detection system on AWS. So we've covered everything from CloudFormation infrastructure deployment to pipelines, from robust data preprocessing and train and machine learning models. So this complete system detects network attack in real time. So continuously learn from new threats and scales automatically. So it's a true enterprise level security technology. Drop a comment with your question or how you plan to use this system. All code, templates, and documentation are linked in the description below. You can download from my GitHub repository. Challenge yourself by training the ML model with your website normal network data, then simulate being a hacker and create different types of attacks. Thank you for joining me on this journey. You now have the skills to deploy ML power security at scale. Until next time, keep building and stay secure. See you next time.